Hello everyone, and welcome back to Introduction to Number Theory. This time we will discuss the decomposition method, which involves some algebraic transformations. Consider an equation you see over here. Well, on the left-hand side we see a quadratic form of a polynomial in two variables, and we need to find all possible integer values of these variables such that the value of this polynomial is equal to 14. First, we decompose the polynomial, we decompose the expression into a product of several smaller expressions. This expression here can be transformed into x plus 2y multiplied by x plus 3y. How to decompose an expression into product of several smaller expressions is another question, so we will not discuss this now. Now we'll discuss how can we use this decomposition to find all possible integer values of x and y. So this product needs to be equal to 14. Denote the first smaller expression by a, the second smaller expression by b, and a multiplied by b must be equal to 14. We can simply consider all possible ways of representing 14 as a product of two integers, because obviously a and b are integers since x and y are integers. But the most interesting part is whether any possible pair of a and b gives an integer x and an integer y. I mean the following. Well, when we take some particular pair a and b, then x plus 2y will be equal to a, and x plus 3y will be equal to b. It is a system of equations, and if a and b are integers, will x and y also be integers? First, we need to study and answer this question, and then we will return to the decomposition of 14 into particular pairs of numbers. Well, in this particular system of equations, y will be equal to b minus a, and x will therefore be equal to, let's say, a minus 2y, or we can simply multiply the first equation by 3 and the second equation by 2 and subtract one from another. X will be equal to 3a minus 2b. So we see that for any integers a and b, x and y are also integers. This might be the case for our system of equations, only our system of equations. In other systems of equations, there can be additional restrictions on a and b and c if there were 3 equations and so on. So in each particular case, you need to deal with these restrictions, and depending on restrictions, the number of solutions of the initial equation can be, well, less than the number of possible decompositions of the right-hand side. And now that we understand that a and b can be arbitrary integers, and for arbitrary integers a and b, x and y are also integers, we can return to the initial equation and find the number of solutions of this equation. So A multiplied by B is equal to 14. Well, 14 can be represented as 2 times 7 and also can be represented as 1 times 14. And there are many other ways to decompose 14 into product of two integers. I will not write them all. We will think and we will reason the overall number of such decompositions. Well, we understand that all other decompositions of 14 into the product of two integers can be obtained from these two decompositions by switching places of factors and by adding minus to each of the factors. So, for instance, we have a decomposition like, well, minus 7 multiplied by minus 2, and so on. So we have really many such decompositions, and we have two really different decompositions, and in each of them we can switch places of factors, which increases the number of possible decompositions twice. And we can also add minus to each of the factors, so each of them is plus or minus, which also increases the number of decompositions twice. So we take two really different decompositions, multiply by 2, which corresponds to switching places, and multiply by 2, which corresponds to adding or not adding minuses before these integers. Eventually, we understand that there are exactly 2 times 2 times 2, 8 possible decompositions of 14 into 8 times b. So there are 8 possible pairs of A and B, which brings us to 8 possible solutions of this equation. So the number of solutions is equal to 8. Which means that there are 8 pairs, ordered pairs of integers x and y. And each of them can be obtained using this formula, applied to any of the decompositions of 14 into 8 times b. Finally, the decomposition method can be used not only to solve the Diophantine equation directly, but also to obtain some additional information about unknowns and to get closer to the solution in other Diophantine equations.